project is called VS4GS Visual Analytic Tool for 3D Reconstruction. The members are Lin Kaiyuan and Hong Feng. 3D is a state-of-the-art method to synthesize and render scenes due to its high quality and real-time rendering. These are some examples of representations of large and unmounted scenes. The process of 3D involves taking SFM points to create 3D Gaussians and through this process to create a 3D scene image. Our focus is on adaptive density control, which happens during training. Under-reconstructed splats are cloned, while over-reconstructed splats are split until they fit the area. However, this is a black box process which is not clear to the user. 3D have issues when artifacts like floaters and blurry patches would appear, and due to the densification process being a black box process, it is very difficult to pinpoint the cause of these artifacts.
First, our system starts with the training module, which generates Gaussian data along with key training statistics. These outputs are then passed into three components: iteration view, data visualization, and the Gaussian tree, allowing users to trace how each Gaussian evolves throughout the training process. And here, 3DGS Viewer provides an interactive scene display for the user to use. Within the viewer, we have the scene model that represents the active 3D reconstruction. Users can use the selection system to highlight specific Gaussians and can use the view count and quality score to visualize camera view coverage and reconstruction quality.
This is the training data visualization. You can add different types of data. You can also remove them. And then this is the iteration view. You can see that it also reflects on the chart, and then you can change it. You can see the scene that it actually changes it. And this now you can see in the Gaussian tree. You can see you zoom out. You can see some nodes, and then if you zoom further in, it'll be gone. So you can further see these details in later discussion.
For the next demo, we have the quality score visualization and the view count visualization. After that, we move to ellipsoid view and test out the single selection. Next here, we have the ray casting selection. And after this, we go on to the brush selection, which has an adjustable radius. Finally, we have the frame selection, which requires us to drag to select.
We implemented the feature to allow the user to see scenes under different iterations during training, which allows them to see the difference of scenes of different iteration. The second feature we implemented is the training data visualization. We offer interactive plots that visualizes training data in a clear manner, making it convenient for users to check in the viewer. We developed a tree structure that can visually represent the densification process of 3D. Left is the zoom out view and the right is the zoomed in view. Here are the four visual representations of the four events, which are clone, split, and prune events. We also implemented hover over node feature where a user can hover over a node in tree to see its information and also highlight a specific node in the scene. Due to the tree being incredibly large scale, we implemented a level of detail feature where some nodes might not be shown based on its perception value. The calculation of the perception value for each node is based on the number of descendants and lifespan versus that of the other nodes in its family. If perception value is greater than threshold, then it will be visible. The threshold is based on the current zoom of the tree view.
Our system supports four selection modes. Single reads the pixel under the cursor. Brush selects Gaussians with a circle. Frame selects Gaussians inside a dragged rectangle, and Ray uses octree-based ray ellipsoid intersection for selecting Gaussians. For the quality scoring, we find the final score S for each Gaussian I, which is the sum of photometric score plus the geometric score, which is then normalized and then mapped onto an inferno color map. For the view count analysis, we find the sum of how many cameras can view a specific Gaussian, and the final view count is normalized and mapped onto a jet color map.
Our viewer achieves good performance with FPS around 110 to 120 FPS depending on the iteration loaded. The performance for the quality analysis and selection system are also good, with the selection able to select under noticeable amounts of time. Computation of scores are also very quick with 262 and 39 ms. By using Gaussian tree, we can visualize scene splats into clear node representation in a tree structure, which gives great amount of insight to the densification process. More detailed areas result in smaller split Gaussians, while larger, less detailed areas like floors contain large cloned splats.
In this case study, we diagnose low-quality regions in 3DGS using view count and quality score visualizations. Low visibility and large splats shown in blue and yellow indicate poor reconstruction. By inspecting the red Gaussians, we find many are oversized or misaligned, suggesting this region needs further densification.
Thank you.